the last lecture of the statistics topic for this course. So would be the season finale of statistics. So in this class, I was hoping that we can finish the regression and correlation analysis, and then hopefully we have some time left that we can do an overview or review of what we have learned today in this whole course. So from last lecture, we started on regression. So regression is different from what you have been introduced for this semester in statistics. It's regression really about correlation between two continuous variables. And then we introduced a little bit about what is a linear regression and what type of linear regressions that you can have. It's really quantified by bigger variance or smaller variance. So the most important thing for regression is you remember or understand the basic format of the full linear regression model. So this is a regression model that each observation, the dependent variable, which is called yi here, is an equation or is a linear component of beta 0 plus beta 1 times xi plus a random error term. So the expectation of y given x is beta 0 plus beta 1 times x. So here y is the dependent variable, and x sometimes is called independent variable, sometimes it's called covariate. So in regression, most of the time we assume that x are given or x is a fixed variable and y is a random variable. So y takes expectation of beta 0 plus beta 1 times x given the pair of x observed. And then y has a random component, and that is epsilon I. So epsilon I really stands for the variance of y. And epsilon I, typically we assume that it follows a normal distribution with mean 0 and variance sigma squared. So that means the distribution of y is also normal. And the expectation of y is beta 0 plus beta 1 times x, and the variance of y is also sigma squared. So this is the key of linear regression. And then we introduce the 4 assumptions of linear regression, which we will revisit today. And then after that, we introduced what is the concept of beta 0 and beta 1. Beta 0 is essentially the intercept term. It's the expected value of y given x equals to 0. And beta 1 is the expected increase of y given x increase 1 unit. So sometimes you can interpret that beta 1 would be the average change in y if x increase 1 unit. And then we talked about how do you estimate beta 0 hat and beta 1 hat given a set of observations. So given the observations, essentially you have a scatter plot of y on the y-axis and x on the x-axis. And you're trying to fit a straight line on that scatter plot. That the purpose to fit that straight line, or what you're trying to do, is to minimize the distance between each of the scatter plot, which is your observations, to that fitted line. So in that way, you basically have an objective function that can be formalized by the summation of squared distance. So the summation means you need to summarize across all the data that you have. So summarize across all the I from 1 to n. And then the squared distance is quantified by yi minus yi hat. So yi hat in linear regression, that is beta 0 hat plus beta 1 hat. So essentially, the objective function is the summation of the square distance, and each square distance is a function of beta 0 and beta 1. And then the most intuitive way to estimate beta 0 and beta 1 is trying to find the values of beta 0 and beta 1 that minimize this objective function. So after you do this minimization, what you get is beta 1 hat is in this formula, which is typically stands by Lxy divided by Lxx. So you can see Lxy, this is just a symbol to represent that it is a sigma of x minus x bar multiplied by yi by minus y bar. And then Lxx would be just the total summation of xi minus x bar squared. So it's a ratio between those two terms. And then once you have beta 1 hat estimate, beta hat 0, you can just plug in beta hat 1, and that should equal to y bar minus beta hat 1 times x bar. So that is beta hat 0. So those two estimates are called the least square estimate. And after that, the next topic is in regression is we're trying to do some inference. And when we talk about inference, essentially we talk about inference of beta hat 1. Actually, no, it's about inference of beta 1, because you have estimated beta hat 1 and you're trying to use your sample to infer that whether beta 1 equals to 0 or not. Because if beta 1 equals to 0, that means there's no linear relationship between x and y. So whenever you talk about inference of linear regression, most of the time you are talking about inference about the slope. And when we introduce inference, we first introduce the concept of decomposition of the total sum of squares. So this is very similar to the concept that we introduced when we learned analysis of variance. Essentially, you decompose the total sum of squares into two components. The first component is regression sum of square, and the second component is a residual sum of square. And the underlying idea is, suppose this is the grand mean, and this is your fitted line, and this is one of your observations. So from this observation, the total sum of squares would be the total square distance from the observation to the grand mean, which is y bar. And then this equals to the summation of two components. The first component would be the sum of the squared distance between this observation and the fitted value. And the second component is the square distance between the fitted value and the grand mean. So the idea of doing inference is essentially trying to test whether this fitted line has a slope of 0, which is close to this grand mean line. Because if it has a slope of 0, that essentially means that this line gets closer and closer to this line. The blue line gets closer to the red line. So that means the second component, which is the regression sum of squares, is getting smaller and smaller in the total sum of squares. So that inspired that a ratio or the proportion of the regression sum of square in the total sum of square. So this proportion is a very important metric in terms of evaluate how strong the linear relationship is. Because if this proportion is bigger, that means you have strong evidence towards a linear relationship. If this proportion is very close to 0, then you have little evidence to see that there is a linear relationship. So we gave this proportion a name which is called correlation coefficient. That is R squared. So R squared is really the proportion of regression sum of squares in the total sum of squares. And it is very natural, straightforward side. R squared is a value that bounded between 0 and 1. And afterwards, we talk about what is the relationship, or what is the relationship between R squared and Pearson correlation coefficient. Pearson correlation coefficient is the square root of this R squared. And you have, different from R squared, Pearson correlation coefficient, because it's a square root, so it can have positive sign or it can have negative sign. And the sign is a sign of beta 1. Essentially, if you have a positive correlation, Pearson correlation coefficient is positive. And then if your correlation is negative, it is negative. However, in terms of R squared, it's always a positive number or non-negative value. And then we'll give you several examples of what are the different R squared values stands for on a scatter plot. There's a caveat that Pearson correlation coefficient actually, in terms of simple regression, it actually is a function of beta hat 1. So remember, we talked about Lxy divided by Lxx is beta hat 1. So here, beta hat 1 actually equals to a function of Pearson correlation coefficient. So whenever the two variable has 0 Pearson correlation coefficient, that implies that if you do a regression line between x and y, the beta hat 1 should be also 0. Okay, I think that's where we stopped last time. So after we talk about how do you estimate beta hat 0 and beta hat 1, the next step is how do you estimate sigma? Because sigma, remember, that is a variance of epsilon, which is also the variance of y. So how do you estimate this sigma? And you can, from this formula, you can see there's one important element that is exactly the assumption of linear regression, is the variance of y is always sigma squared, no matter what is the value of x. So this is what we call equivariance assumption. Essentially, the variance of y is constant in terms of different value of x. So in a scatter plot, you can understand in this way. Suppose this is y and this is x. And this plot stands for there is a linear relationship between y and x. And this function, by assuming yi equals beta 0 plus beta 1 times xi plus epsilon I, and epsilon I follows a normal distribution with sigma squared. Exactly what that means is the spread of y at each value of x is constant. So that means y is only a function, or y only has a linear relationship with x in terms of the mean level, on the mean level. However, the variance of y stays constant, because from this one, you can basically see that the variance of y is just one value. It's independent of x. So this is one very important element of linear regression, because the variance stays the same. This doesn't matter whether what value is beta 1. It could be that y doesn't have any relationship with x. But no matter what is the value of beta 1 or what is the value of the slope, essentially the spread of y is independent of x. So this is a very key element of linear regression. And along the line, you will see, you probably will have chance to see generalized linear regression. And why do we have generalized linear regression, which is a step beyond linear regression? And the main reason to handle that is for generalized linear regression, not only y has a mean, the expectation of y has a linear regression with x, but also the variance of y change when x change. So that is essentially beyond. So suppose you have this kind of relationship that when x is small, there is an increase in trend that x increase, y also increase. So that is on the expectation level. However, you can also see that on the variance level, when x increase, y also increase. So for this type of data, when you see a scatter plot in this shape, essentially it implies that linear regression or simple linear regression can no longer handle this. Because linear regression has this very important assumption that it's a constant variance. And for this one, that is why statistics bothered to introduce the concept of generalized linear regression to handle this type of data. And especially when you talk about RNA-seq or even microarray, sometimes without log transformation of just the count data of RNA-seq, a lot of times you encounter the situation that y, not only the expectation level is a function of a covariate. On the variance, it's also a function of covariate. So in that way, remember, you either need some transformation to make it constant in terms of variance, or you have some more complicated procedure for doing regression. So remember, one characteristic of linear regression is constant variance. And here we are going to introduce how do you estimate this constant inference. So this is actually fairly straightforward until this step that we have learned, because we have y, which is observed value, and then we also have the fitted value, which is y hat. Y hat is beta 0 hat plus beta 1 hat times x. So in that way, your residual on each of the observational level, you can see that epsilon I hat equals yi minus yi hat. So that means for epsilon I hat, it's in this formula. Just plug in the estimated beta 0 hat and beta 1 hat and plug in for each xi. You got this distance, and this distance is epsilon I hat. So on the linear regression scatter plot, what you have is, if you have this observation and then you have this fitted line, which is y hat, and this would be yi. So the distance between your observation and your fitted value is epsilon I. So this is your residual. And then how do you estimate sigma square? So that essentially is, you take the summation of this epsilon I hat and you divide that by n minus 2. So it's summation of this term. So sigma square hat, the estimate of sigma is yi subtract yi hat. Take the summation. This summation over n minus 2. So this would be the formula to estimate sigma square hat. So you can basically see that so this is, sometimes we put it in a symbol called SYX. And this SYX is essentially a sigma hat. So you can see that it is in the format of residual sum of squares over n minus 2. And residual sum of squares is sigma of y minus y hat squared. And like we said before, what is this sigma square, or what does this metric stand for? So this metric, or this measure, is really the variation of the observed value from the regression line. If there is a smaller sigma square, that means all the observed value are very tightly clustered around the regression line. On the other hand, if you have estimate of a very large sigma square, so that means there is a wider spread of the observation to the regretted line, to the fitted regression line. So this can also be understood from here. Essentially, if the total sum of the squared sigma I is small, that essentially means that all these observations are very tightly clustered around this fitted line. On the other hand, if this square distance is longer or it's bigger, so that means all those observations are further away from this fitted line. So this fitted line is still in the middle of all the points. It's really just about the sigma square is a measure of how tightly those points clustered around this fitted line. And after we have the sigma square, actually, you can use that to represent the standard error of the regression slope of beta hat 1 and beta hat 0. So previously, we talked about how do you estimate beta hat 1 and beta hat 0. And there's a key element that beta hat 1 and beta hat 0, it's like the mean. It's a statistic. So for any statistic, there is a point estimate. There's also a variance estimate or standard error estimate. So the standard error of beta hat 1 is in this formula, which is SYX over square root of LXX. So remember, SYX is sigma hat. So like we talked, residual square, sum of square over n minus 2 takes the square root. And then LXX is a summation of the square distance of xi. Okay, so this is the standard error of beta hat 1. And then beta hat 0 would be the standard error of beta hat 0, which is in this formula. So again, it is a function of the sigma hat. Sigma hat square multiplied by 1 over n plus x bar over this term again. So until this step, we have introduced that in a simple linear regression where y equals beta 0 plus beta 1 times xi epsilon I. In this formula, beta hat 1 equals Lyx divided by Lxx. So some formula that you plug in. And what is the standard error of beta hat 1? So this is a point estimate. And this is the standard error estimate. That equals to SYX over LXX squared. So in other words, if we have beta hat 1 in this point estimate and in this standard error estimate, we can actually know what is the mean and what is the variance of beta hat 1. So beta hat 1, in this formula, if you work out what is expectation of beta hat 1, that is beta 1. You can do some algebra and you can eventually see that this ratio, the expectation of this ratio equals beta 1. So beta hat 1 is an unbiased estimate of beta 1. And then the standard error of beta hat 1 is in this formula. So this is the variance, which is the square of this formula. So this is the distribution of beta hat 1. And beta hat 1 would be a normal distribution if you know the variance. However, because here you substitute the variance by the estimate, so the price that you need to pay is, instead of a normal distribution, beta hat 1 should be a t distribution. And you got the mean and the variance. Okay? And similarly for beta hat 0, so this would be the point estimate of beta hat 0, which is y bar subtract this beta hat 1 multiplied by x bar. And then you have a beta hat 0, the standard error estimate, which is in this formula, xi. So you got syx squared, and then you have 1 over n plus x bar over lx. So it doesn't have this part. So this would be the standard error of beta hat 0. So after this, you can basically see that beta hat 0 has a mean, which is beta 0. Beta hat 0, you can work out the expectation of beta hat 0. It's also unbiased estimate, which is beta 0. And then the variance is the square term of this term. So after we have learned the distribution or the mean and the variance of beta hat 1, and we also introduced a little bit that beta hat 1 should be a t distribution. The next step is, given this, we can actually do some inference about beta hat 1. Because remember, when beta equals to 1, that stands for the linear regression doesn't hold. So there's no linear relationship between y and x. So that essentially means that we can use beta hat 1 to do inference on beta 1. So intuitively, or in a graphic display, what does this s beta hat 1 stand for? So this is really stand for how variant, or what is the variation in the slope of the regression lines from different possible samples. So if you have a small standard error of beta hat 1, it basically means, like if you have this set of 20 samples, you got a regression line, and then you have a second set of 20 samples, you got another regression line, and then you get several regression lines in that way, and each of those are actually do not vary quite a lot in terms of their slope. On the other hand, if you have a very large standard error of beta hat 1, that means the slope from each sample site would be very different. So, like I said, once we know the distribution of beta hat 1, we can actually use that to do inference. And what is the inference here? The inference is a population it's a test on the population slope on beta 1. So remember, this is actually a fairly common mistake. Like I sometimes make this mistake. But remember, when you do inference about the slope, you're not doing inference about beta hat 1. You are doing inference of beta 1, which is a population slope. And scientifically, it means that whether there is a linear relationship between x and y. So the null hypothesis is beta 1 equals to 0. So that stands for there's no linear relationship. And the alternative hypothesis means beta 1 does not equal to 0. So this is a two-sided test. It doesn't matter whether it's positive or negative correlated. As long as beta 1 doesn't equal to 0, that means there is a linear relationship between x and y. And what is a test statistic? Like I said, we can utilize the sampling distribution of beta hat 1. So beta hat 1 should have this mean and this variance. And we know it's a t distribution. So we can use that to see beta hat 1 subtract beta 1 over the standard error of beta 1. That term should be a t distribution with n minus 2 degrees freedom. Yes? Could you see that thing? Good question. So the total n is the total observation. Total number observation. And then remember when we do sample estimate, when we do sample variance estimate, we use n minus 1. So that means you use 1 degrees freedom to estimate the grand mean, right? And then here we use n minus 2. That is, in addition to the grand mean, you also have used 1 degrees freedom to do the y hat. Okay, so essentially from n, you use 1 degrees freedom to do y bar, and then you use another one to do y hat. So your effective degrees freedom is n minus 2. You can see that more clearly from here. That you have total sum of square, regression sum of square, and residual sum of square. So this one, you decompose the total sum of squares into the two components, right? And like we talked about in analysis of variance, you can also do that for the degrees freedom. So total sum of square equals regression sum of square plus residual sum of square. So this is on the variance level. In terms of degrees freedom, how does that decompose? Total sum of square, the degrees freedom is n minus 1, right? You have n observation and you have y bar here. So you subtract 1. So that is n minus 1. And then regression sum of square, that is 1. Remember, that is always 1 because you use this linear regression to estimate y hat. So this is 1. And then your residual sum of square should equal to this term, subtract this term. So that is n minus 1 subtract 1. So this part is n minus 2. So essentially, in your residual sum of squares, you have n minus 2. That is a degrees freedom associated with sigma square. So that means for this term, you have n minus 2 degrees freedom. And that means for this term, for the standard error of beta hat 1, you have n minus 2. So that means the t distribution of beta hat 1 should be n minus 2. Okay, so the t statistic equals beta hat 1 subtract the null hypothesized value over this s square standard error of beta hat 1. So in practice, how do you express that? Is the t statistic equals the estimated beta hat 1 subtract the null hypothesis value of beta 1 over S of y of S of beta hat 1. So if you plug in all the values, and this one should equals to S. So this would be how you calculate manually what is the t statistic. And most of the time, this is 0, so this disappears. And sometimes, this one actually has pretty much freedom of flexibility that you can also test a non-zero null hypothesis. Suppose you see that this is my y and this is my x. Suppose this is two measurements of the same quantity. So your null hypothesis now is not that y and x should be no correlation. Your null hypothesis is essentially that when x increases 1 unit, y should exactly increase 1 unit. So your null hypothesis is the slope is a 45 degrees line. So you could have different value. So in that way, your test statistic is just beta hat 1 subtract beta hat 1, 0, which is 1 in this case, and over S. So essentially, this formula doesn't really just be restricted to test whether the slope equals to 0. It can really be flexible in terms of test any hypothesized value of the slope. Remember that. Okay, so going back to that children growth example, so we have the null hypothesis is the children's height increase has no relationship in terms of their age. So beta 1 equals to 0 in this case. And the alternative hypothesis is beta 1 does not equal to 0. And the t statistic is beta hat 1 subtract beta 1 over the standard error of beta hat 1. So beta hat 1 here is estimate is 64.93. And then the standard error estimate is 0.5. So we got the t equals 127.7. So this is a test statistic. And from this test statistic, it's very obvious that we have 12 observations. So the degrees freedom is 12 subtract by 2, which is 10. So it's very obvious that we are able to reject the null hypothesis that there is very sufficient evidence that children grow over time. So this is quite an obvious example, but essentially you can use this formula to test any of your hypotheses in terms of linear regression. And whether you use Python or you use R, you will have an output of a test of linear regression whenever you do a linear regression estimate from those software. And that is exactly testing the hypothesis that whether the slope equal to 0 or not. Okay? So that concludes the second topic that we want to introduce about linear regression, which is on inference. So remember, for inference, we talked about two important concepts. The first concept is what is a ratio to quantify the linear relationship between two variables, and that is called correlation coefficient. And the correlation coefficient essentially is defined in terms as on the basis of linear regression, which basically means that it's a ratio of regression sum of square over the total sum of square. And then we talked about how do you do inference of regression. And essentially what we mean here is how do you do inference about beta 1? Because when beta 1 equals to 0, that stands for no linear relationship between y and x. And we can use a t-distribution, or we can use a t-test to do that inference. And that inference take advantage of the distribution of beta hat 1 as a t-distribution with the mean at beta 1 and the variance at the standard error estimate. Okay. And before I move on, I really want to emphasize one thing is the Spearman correlation coefficient. Remember that when we talk about Spearman correlation coefficient, out of the context of linear regression, you always think that Spearman correlation coefficient is a metric of how correlated the two variable is. And now you understand that Spearman correlation coefficient is a square root of the correlation coefficient, which is that ratio. So now I hope you understand that Spearman correlation coefficient is more precisely, it's a measure that quantify the linear relationship or the linear correlation between two variables. When a Spearman correlation coefficient is 0, that not necessarily mean that the two variables are completely independent or completely uncorrelated. It just means that there's no linear relationship between those two variables. So this is a very common mistake that people make, because sometimes if you have a quadratic correlation between two variables, it's not linear, but you cannot see that they're not correlated. And quite often in those situations that Spearman correlation coefficient between those two variables are actually fairly low. So I hope you can remember after this course that Spearman correlation coefficient really just to quantify the linear relationship between two variables. And I want to introduce a little bit, in addition to, which is outside of the context of this lecture, is we talk about parametric methods and non-parametric methods. And pretty much for most of the methods, when we introduce a parametric way, we also introduce a non-parametric way, which handles a non-normal distribution or small number of the observations or outliers. So we talk about the Wilcoxon sign rank test or Wilcoxon rank sum test, and we introduce that those are the alternative of their parametric versions. So for Spearman correlation coefficient, there's also an alternative of non-parametric method. That is called, for Pearson correlation coefficient, there is also a parallel non-parametric version that is called Spearman correlation coefficient. Let me write down the name. So this is Pearson correlation coefficient, like we talked. R equals square root of R squared with a sign. Okay, so there's also a non-parametric version that is parallel to this one, which is called Spearman. This is a non-parametric one. And this is a parametric one. Because essentially, this one, you're making some assumption of the data, either X or Y, is coming from a normal distribution. Or you have sufficiently large enough sample size. But what if you do not have that? What if you have very strong outlier? That, for example, if this is your Y and this is X, and you have this outlier, which is an outlier in both Y and also X. Without this outlier, there's pretty much no correlation between X and Y, but having this outlier, it really heavily influences your inference about the linear relationship between Y and X, because having this outlier, your fitted line might be like this, right? So this is the line, this is the regression line between y and x without this one outlier. And then with this outlier, it actually, sorry about that. So with this outlier, you actually heavily influence the fitted line between y and x. So this is an example that there is presence of outlier. And in this situation, if you use Pearson correlation coefficient, you would actually bias, or you would have a very impacted estimate by these outliers. So sometimes people in those situations, people would consider to use non-parametric version of correlation coefficient, and that is called Spearman correlation coefficient. So essentially how does Spearman correlation coefficient work is, what about you just ignore all the value of x and y? You just get the rank of from y1 to yn, and then you got the corresponding, so x and y still doesn't change. The pair relationship doesn't change, but you just get the rank of y, and then you plot. So this would be the rank of y, and this one is the rank of x, and then you want to see whether there's correlation between the rank of x and y. The underlying concept is, if there is a linear relationship between y and x, so that means the y that is associated with bigger or higher rank of x should also be higher rank in y. So if there is a linear relationship, that linear relationship should also be reflected on the rank level. So if you just ignore the actual value and just get the rank, and you can do a Pearson correlation coefficient on the rank instead of on the actual value, that is the Spearman correlation coefficient. So Spearman correlation coefficient essentially is a correlation coefficient on ranks. It's like ANOVA, that the parallel non-parametric test is called cross-bodies test, which is ANOVA on the ranks. So that is exactly the same idea. And for that situation, Spearman correlation coefficient can pretty much handle this outlier, because although this outlier is far away from the rest of the data, the rank of this outlier is actually, among the same magnitude of the other observation. So that doesn't really impact, or that doesn't really have that much of influence. So Spearman correlation coefficient is more robust in terms of outlier. It's very similar to the other situations where you decide whether you use a non-parametric or use parametric. So if you have outlier presence and you see that your Pearson correlation coefficient is heavily driven by outliers, then you should use maybe a Spearman correlation coefficient. Or if you have the sample size that is far from normal distribution, then it's a good situation to consider that as well. Or if the sample size is too small. We talked about what if you have ordinal data. The ordinal data doesn't have to be two data are both ordinal. Like there's a study that I was involved in, and for that study, they have a biomarker, which is a gene expression of TP53. And for that one, it's our mRNA data, so it is a continuous data. And then they have a clinical trial that is targeting on P53, the protein. So in their outcome, they have similar outcome, which is like complete response, partial response, and non-responder. So they have some of those. So in that situation, they want to ask the question is, what is the correlation between this biomarker, mRNA biomarker, and outcome response? So in that situation, although you have x-axis, which is a biomarker, is a continuous variable, your y-axis, it's very hard for you to translate those categories in terms of the actual continuous number. So in that way, you can get the rank, like we talked before, right? And then essentially you have like this. And this one, if you want to get a correlation between outcome and the biomarker, you should only use Spearman correlation coefficient. Because this rank, although you use some continuous value, it's not the actual value that stands for the outcome. You're taking the rank. And then you take the rank of x, and you got the correlation coefficient between the two ranks. And then that is a Spearman correlation coefficient. So that is a situation that you have to use a Spearman correlation coefficient.
Can I ask an extreme case, for instance?
Sure.
Like we have high sample size, but there are so much outliers, so would you prefer to use smaller?
Because there are so many outliers, for that situation, probably a non-parametric Spearman correlation coefficient would be more appropriate because it's more robust to outlier. Okay, so the last topic in regression is how do you, after you fit the regression, how do you revisit the regression and revisit the assumption, those four assumptions. And those four assumptions, remember, what we call linearity, independence of errors, normality of error, and equivariance. And this is important, and this is most of the time, this step is ad hoc. Basically, it means that you do not do the step until you finish the fitting between y and x. So you fit a regression, and then you revisit those four assumptions, and you see if those assumptions hold or do not hold. Sorry about that. And then, so this is called residual analysis. So residual analysis, essentially it means that you assess those four assumptions on the level of residual. And residual, remember, our definition is epsilon I equals yi subtract yi hat. And then how do we use this epsilon I to estimate or to assess those four assumptions? Essentially, there are no formal tests of any assumption. It's really about graphical visual inspection of those residuals, and that can give you some hint about any of those assumptions hold or not. So let me give you a little bit tool of how to use that. So here, the first assumption is linearity, which stands for L. So linearity, it means that the relationship of the mean of y should be a linear function of x. And only that hold, it is appropriate to use linear regression. So on the y level, if you plot a scatter plot of y versus x, you are expecting this situation instead of this situation. If you have this curvature behavior between y and x, then probably linear regression is not a good choice. And you can actually see that more obviously on the residual plot, because once you get epsilon I equals y minus y I hat. So you plot the y-axis this time to be epsilon I instead of yi. And then so you plot epsilon I versus x. And on this plot, what are you looking for? You're looking for a random distribution of the residual as a function of y, as of x. So from this two plot, this plot translate into this part, and this plot translate into this part, because the curvier behavior translate on the residual level, it's still curvier, and this basically means that the relationship between y and x is not linear. However, if this is completely random, that there's no trend of going down or going up, or has a curvier or the other type of relationship, so that basically means that your residual has a random pattern in terms of when x change. So essentially, on this plot, what does that mean? That means for any of the residual from any observation to the fitted line, it's random. It could be positive, it could be negative, but there's no systematic trend. Okay, so this is the first diagnostic of linear regression, which basically when you plot residual versus x, you're looking for some random pattern here. Okay, so what is the next assumption, which is independent? That means independent means each of the yi should not impact the y that in front of this or after this. Each of the yi, especially the residual, like this residual doesn't have any impact on the other residuals. So this is called independent. So similarly, on this plot, what you're looking for is, again, a random cloud. And if you have this situation where whenever you have x increase, more likely y increase, but also at the same time, the next y, like when the y that are associated with bigger x are more likely to be very close to the y that very next to, right before this one. So if you do this way, if you plot the residual of this one, you can see there's a pattern there's a trend of y with respect to x, whether it's this trend, like have a periodic trend, or it has like increasing monotone trend. Both of the situation means the errors are not independent. So conceptually, when is it possible that you have non-independent observations? Most likely, if the data is from longitudinal observations, or if the data is from time series, most likely this independent assumption does not hold. Because for time series of data, y, most likely, like y in this day, will impact y in next day. Like for instance, if you look at stock exchange value of our index, like if today is increasing, most likely tomorrow is also increasing. And then if you have a decrease in terms of y, most likely the next couple y's would also decrease. So that means y is not only impacted by x, it's also impacted by the previous y and the next y, or the next y. So in that situation, this is typically called a time series data. In that situation, most likely you do not have independence assumption, or you cannot use independent assumption. So that is, in statistics, that is called longitudinal data or time series data. And remember, if you have like experiment and you measure the biomarker level of you, or you measure some level that a long time, you cannot use a simple linear regression to model that data because it violates the independent assumption. So this is the second one. And the next one, which is called normality. And before we go to this one, let's do the last one first. So the last one is called equivariance. So equivariance, like what I said, it essentially means y is a function of x only on the level of expectation. On the level of variance, y is constant. It doesn't matter how x change, the variance of y should always remain constant. So if you have a y versus x scatter plot, if you have this situation, which is more likely to be like Poisson data or count data, this essentially means you cannot use linear regression without any transformation because this violates the equivariance assumption. Only if you have this situation that the spread of y is constant no matter how x change, this means you have equivariance. So when you translate that into residual plot, residual versus x, when you have this situation that the residual gets inflated or deflated when x increase, that means you have non-constant variance. And what you're looking for is it's a random cloud that has the same spread across different values of x. Okay, so we have talked about 3 assumptions. And in those 3 assumptions, remember, all you're looking for after you do regression, the next step, the last step, or whenever you do a regression, the last step is plot your epsilon I hat, which yi equals minus yi hat. Plot this one on the y-axis and plot x. What you're looking for is, suppose this is 0. What you're looking for is a random cloud around 0. Because only if this holds, this pattern holds, that means the relationship between y and x is linear. That also means, most likely, each yi is independent. It also means that the variance of y is constant in terms of x. So this one plot can give you a hint about those 3 assumptions. So the last assumption is normality. And here we are going to teach you a useful plot, which is called QQ plot. So QQ plot is a plot that can be used to assess whether your data, your observed data, follows a certain distribution. Especially what we are talking about here is you can use QQ plot to check whether the data of y follows a normal assumption. So this is called a normal probability plot, or a QQ plot of normal distribution. So you can do a QQ plot of the residuals, because the residual, remember, it should be normal distribution with 0 mean and sigma square variance. So you can do that, and what you're looking for in a QQ plot is a strict line. So all the data points, which is your residuals, should be centered very closely to a straight line. Because if it fits a straight line, that means the residual is approximately normal distributed. So you can do this experiment that if this is your residual by a histogram, you have a histogram of residuals, which is similarly, very close to a normal distribution. And then if you do the same residual on the QQ plot, you basically can see that there is those dots, those observations of residuals are very tightly around the straight line. So this stands for that the normal assumption holds. On the other hand, if you have a residual which is very far from the normal distribution, like this part, if you do a QQ plot, what you will look like is the residual has a very big deviance, or it's very different from the straight line. Either it's this shape or the other shape. As long as it's not on the straight line, you have some doubt that whether the residual is really normal or not normal distribution. Your residuals versus the expected quantiles of standardized normal distribution. So I'm not sure how to do that in Python, but in R it's actually it's called QQ norm. And then you just do your X, which is your residual, which is your epsilon I. If it's a vector of residual, you just do this function, QQ norm. It typically gives you this QQ plot. This QQ plot is essentially your observed value residual on the y-axis, and then the expected quantile on the x value. Here, because you're comparing to a normal distribution, so this is the expected quantile under a standard normal distribution. And you're looking for is all the dots are closely clustered around a straight line. Okay. So, I think this is just some more example of non-constant variance. So this is a more example of this y in x. It has this non-constant variance. You can see there's this shape of variance increase as x increase. So when you see in terms of the residual versus x plot, it's more obvious, like there is this shape or trend that the variance of residual increase when x increase. So this is an ideal residual plot where you have no nonlinear trend, you have no curvature or no impact from previous observation or later observation, and that you have constant variance. So this one just gave you a little bit of, in terms of diagnostic of linear regression, after you diagnose those 4 assumptions, which is the line assumption, the next one that you can also do is kind of some outlier diagnostic. For example, it could have several, scenarios of outlier. So this part, this plot, you have all the observations except this one right here, and you have this one observation here. So this one, you have outlier in both y and x, but it's a non-influential outlier because this outlier is in the faded line, and the faded line fit the others as well. So this one, this A, would be a quite influential outlier, because this whole straight line, the whole faded line, is pulled up by this one observation, right? And those two, this situation is also an influential outlier. So you can see that without this outlier, actually your data is very different from the pictures that with this outlier. Without this outlier, there's actually no relationship between y and x, right? And this part is Actually, there are not only one outlier, and there are two outliers. And those outliers actually they cancel out each the effect from each other. So here, the purpose of showing different examples of scenarios outlier is not really to teach you what do you do when you see those situations. It's really just give you some examples like what might happen in practice. And this will be helpful for you to do any linear regression is do a scatter plot of y versus x. When you see an outlier, you probably want to go back and revisit your data to see if there's either any error associated with that outlier, or if there's anything that atypical that happens to that observation. If you cannot rule any of those out, and you can do what you can do is called sensitivity analysis. Basically, you fit a regression with the outlier, and then you fit without the outlier, and then you compare like what is the impact from this outlier. So here we just give you a little bit strategy or some advice in terms of how do you do regression. Whenever you do regression, you can start with a scatter plot of x versus y, because this will not only tells you whether there's a linear relationship between x and y, it also tells you whether any of those assumptions or any of those outlier is valid or present. And then after you examine those assumptions, you can estimate regression coefficient, and then you can do inference. And after all those steps, you can do a residual plot to check the the model assumptions. And last but not least, we actually learned how to make predictions based on regression, because your prediction is just y hat equals beta 0 hat plus beta 1 hat times xi. So this would be your prediction of y. But so linear regression really tells you quite a lot about your data, because if this is x and this is y, and then this is your observation, and then by this faded line, pretty much you can predict every y for every x, even if you do not have this actual x that observed. Suppose there is this xi that this xi is never actually observed, but as long as this xi is in this range of your total x and y, you can still predict yi as beta 0 hat plus beta 1 hat times x, which is a new x. But what we want to emphasize at the end of this lecture is most of the time when you do linear regression, you have a range of x and y. And you do inference or you do this faded line estimate only within this range, right? So if you want to make prediction of any yi that is associated with x, that is within this range of x, that is fine. But if you want to make assumption or make prediction of y that is associated with x that is outside of this range, you need to be a little bit cautious, because you actually do not have data to support whether or not there is the same relationship between y and x outside your data range. For example, in that children growth example, we have data that from probably like from 15 months to 34 months. And then we have the height, which is like in a very perfect linear relationship between the height and the age. And after you have this data, you can make predictions of what is the height or expected height given a baby is 30 months. That is fine. However, if you want to make assumption of what is the height, expected height, given a baby or given someone who is 30 years old, this is an example of rather extreme, but it tells you that if you want to make assumption or want to make prediction of the height for a 30-year-old person from this data, you have very little confidence or you have very little ground to make that prediction because you don't really know what happens after 34 months. Most likely, the growth rate will decrease, will plateau a little bit. So you cannot just plug in this formula that you get from here until some data point, which is here. That is very dangerous. So in statistics, we typically avoid to make this type of prediction. Okay, and then we talked about, after you do those diagnostic, there are something that you can do if any of those assumptions do not satisfy. The first way that you can do, which is quite common, is to do transformation. So this could apply to both transformation of x or transformation of y. So essentially you transform x and y or x or y into a new variable, and for that new variable, the linear regression assumption is more satisfied. So for example, when you do like a lot of mRNA data, especially from microarray, log transformation of the expression is quite often used when you model the gene expression relationship with other covariates. And that is because if you do not use, if before the log transformation, most likely those y data are not normally distributed. And after the log transformation, it's more likely or it's more similar to a normal distribution. So log transformation is a very typical usage to remove the heavy tail distribution influence. And some examples of transformation, log transformation or square root of transformation, or you can take the 1 over transformation. But there are a lot of restrictions to those transformation as well. For example, for both log transformation or square root transformation, it can only apply to positive number, right? And the goal of those transformation is really first trying to stabilize the variance of y, or you're trying to normalize y, or you're trying to make the relationship between y and x more closer to linear relationship. And that's how we have talked about linear regression. So essentially what we talked is, what is a linear regression? How do you estimate a linear regression? And how do you interpret linear regression? And then last but not least, how do you do inference? And how do you assess assumptions of linear regression? Okay, so that's it for linear regression. And we have about 5 minutes left. So I want to just structure a little bit about what we have learned during this whole course. So during this whole course, except for the first 2 lectures, which is on probability of distribution, which is really a basis of statistics that to prepare you for the next few couple of lectures. Essentially, we gave you some tools of what are the statistical methods that you can use for different purposes, right? So, for example, we talked about what is continuous variable. We talked about what is categorical variable. And then essentially, if you have like categorical variable, we gave you some tools to do correlation of categorical variable. That is for contingency table as a way to display your data, and then you can use chi-square test or Fisher exact test to test whether the two categorical data is independent or not, or whether the two categorical data have any association or correlation. So that is what you do for categorical data, right? And then if your data is not categorical, if your data is continuous, and for that we have learned two purposes. One is, what if you want to do correlation? So for correlation, it really means that if you have two continuous variables and you want to see whether or not they're correlated, so for that, the tool that for you to use is called regression. Right? So regression can really enable you to assess whether X and Y have any correlation. And for regression, we learned how do you estimate the parameters, and then essentially to test or to do inference on regression, it's a t-test of beta 1. Right? So that stands for whether there's a linear relationship between X and Y. And we also talked about correlation. In addition to regression, you can actually estimate some Spearman correlation coefficient, or Pearson correlation coefficient, or just correlation coefficient. So that is related to linear regression, but it is really more it is more called correlation. So for continuous variable, when you're talking about independence between continuous variable, you have correlation or you have regression. And for regression, you can test. For those correlation, it's give you a measure of how correlated the two variables is. Okay? And also for continuous variable, we have talked about difference. How do you compare difference under different conditions if the outcome is continuous variable? So for that, it is not on correlation. It is rather to infer the difference between each condition. So for that, we have learned three scenarios. One is one population, and the other one is two population, and the last one is more than two population. So it really enables you, I'll give you the tool to do all the type of difference, whether it's from one population, two population, or more than two. And then if it's from one population, remember all those scenario, we are talking about difference of mean for parametric method, right? So for parametric method, remember we talked about the assumption is either you are willing to assume the normal distribution, or if n is sufficiently large enough or big enough, you can use mean to do inference. And then for one population, it is called one sample t-test, right? And then for two population, if it's paired, it again goes back to one sample t-test. If it's independent, it goes to two sample t-test. And two sample t-test, more trivial if you're willing to make different assumption in terms of their variance. You can use an equal variance assumption to get pooled estimate of two sample t-test. You can use an unpooled or separate estimate of different variance, or you can no, actually we only have this. And then this one you need to modify the degrees freedom a little bit, right? So, and then for two population, after two population, we talk about three or more population. So those one, we only introduced independent scenario. And for independent scenario, we talked about, which is ANOVA. ANOVA, remember, it assume normal distribution of each population, and also it assumes equal variance of each population. And then it is decomposition of the total random variance, of the total sum of squared. So this is when you test the difference of mean. Suppose you do not have that assumption. Suppose you have small n, you have non-normality, suppose you have ordinal data. What if those situations, under those scenarios where you do not have any of those assumptions or one of those assumptions hold, what is the scenario that, what is a parallel test that you can use to mimic those tests? So for one population or paired two population, the test that you should consider in terms of non-parametric test is called Wilcoxon signed rank test. And then if you have two independent populations, again, you have those assumptions like small n, ordinal data, non-normality. For that, you have Wilcoxon rank sum test. And then for ANOVA, we did not introduce, but you can do a Wikipedia or do some search, and this is called cross-valence test. Remember, the whole essence of those non-parametric tests is you take the rank first, and then you calculate your statistic based on the rank instead of based on the actual value. So we talked about the non-parametric test is more robust, it's more flexible in terms of outliers, in terms of smaller sample size. But the price that you pay for doing this is you would have less power if both of those two tests satisfy. You would have higher power to reject your null hypothesis compared to, if you do a t-test compared to if you do a non-parametric test. Here, the price that you pay is really you sacrifice your power. Okay, so and then that what we talked about here is suppose you have outliers, suppose you have non-normality or ordinal data, and you still want to get the correlation estimate between two variables. For that, the non-parametric test is called Spearman correlation coefficient. That is a non-parametric test. Okay? So, essentially, what we have introduced: one test, two tests, three tests, one sample, two sample, t-test, or ANOVA, and then their corresponding non-parametric version. And then we talked about regression. We talked about, so this is Pearson correlation. So we gave you all those tools. And remember, in the first lecture I told you, statistics is really not a recipe book. It's not like I have those tools and I can start doing my bakery according to this instruction and that instruction. The key for you to remember and the key for you to benefit from this course is really to understand what is the scenario and what is the purpose for using different tools. And using each of the tools, what are the assumptions that I need to be careful and I need to revisit. And then we talked about chi-square test, Fisher exact test, and contingency table. And so essentially, all those we have gave you those options that you can do test. Further on, if you want to further explore, beyond this course, what you can extend, or you can, do some research by your own, or if you want to take further statistics class, what you want to learn is what happens beyond simple regression, because most likely you have more than one covariate, and you want to see if, how together they decide or they predict the response variable. So for that, you need to go beyond simple regression and go to multiple regression. And going that, what is beyond that is called generalized regression model. And generalized regression model really enables you to model non-normal distributed data when you're, especially for your dependent variable. So remember, when we talk about the normal assumption in regression, most likely we are talking about the distribution of the dependent variable. So it's y. So what is y coming from 0, 1? A binomial distribution or Bernoulli distribution. So for that, you need to use logistic regression, which is probably a lot of you are already familiar with. And what is y coming from a Poisson distribution or negative binomial distribution? So for all those, you need to use generalized regression to model that. And then what if your y comes from longitudinal data? For longitudinal data, you do not satisfy the independence assumption. So for that, you need to use mixed effect regression. Mixed effect model. So those are the further steps that you can go beyond. And then, so those about correlation. In terms of difference, let's see, if you do, after you do ANOVA and you want to assess like what exactly is the difference that contributes that you are able to reject the null hypothesis in ANOVA, then what you want to do is doing some contrast between each specific groups or each combination of the groups. And then doing contrast, that has a very important concept of multiple test correction. Multiple test correction really means that when you do your hypothesis testing so many times, do you have some protection in terms of protect your alpha or in terms of protect your type 1 error rate? So that can be extended to a really extreme level for bioinformatics when you have RNA-seq experiment, when you have macro experiment, that you have thousands or tens of thousands experiment, and you're looking for which gene or which protein is different between those groups or between conditions. So essentially, you use this multiple test to extreme, that you use that thousands of times. And for that, you need to use some metric, some method to control your type 1 error rate. So we introduced a little bit on Bonferroni test. But that is really the first step. You could have other choice, like what we call false discovery rate. So false discovery rate is really allow you to be more flexible to adjust your type 1 error rate. Okay, so that is some other topics that you could explore. The other test that could also benefit you in your future is called machine learning. I think in one of the lectures in this course, you will learn about machine learning. And when you talk about machine learning, it's more stepping from statistic to computational methods, that you not only have those rigorous statistics, you but also have computational heavy technique that allows you to do more advanced inference or prediction. So those are basically what we have learned. The red circle is the tools that this course have introduced you to. And then the red words basically means that you haven't learned in this course or in this statistical part of the course, but would be some options for you to learn in the future. And remember, those black branches are the scenarios that to decide when you should use which test. Okay, that's it for today. Thank you. Oh, I haven't.